Hello dear students, welcome you all. In this lecture, I am going to perform the next experiment on virtual lab, right? The experiment that I am going to perform today, it is to find the energy band gap of a semiconductor, right? You can see here, it is written to find energy band gap of the semiconductor, or in some books you can find it as a to measure the reverse saturation current of a p-n junction diode at various temperatures, and then to find the approximate value of the energy band gap of a semiconductor. So this aim can be written in that way. What the thing is very clear, that in this experiment we are going to calculate the approximate energy band gap of the semiconductor. Energy band gap means the gap between the valence band and conduction band, right? So if I go to the theory part, you can see here, you know very well that in solid state physics we know that in case of insulators there is a wide band gap between the valence band and conduction band, and it is of the order of 3 electron volt to 7 electron volt or even more in case of insulators. But for semiconductors this band gap is quite small. You can see here, in case of germanium it is 0.7 electron volt, and in case of silicon it is 1.1 electron volt, right? So actually even for the different semiconductor materials it can have different values, right? But these two are the prominent ones, silicon and germanium. So we should remember the value of the energy band gap. I can show you here the diagram from where you can get the clarity. This side is energy, right? You can see here. Now here you can see that in case of metal there is complete overlapping of a valence band, right, and a conduction band, right? In case of semiconductor there is a gap between energy gap between the valence band and a conduction band, but this gap is small. But in case of insulators this gap is wide between valence band and a conduction band. This gap, as I told you, that it is more than 3 electron volt, right? But in this case it is of the order of 1 to 3 electron volt, or even less than 1, right? We have seen. So this gap is very small. So that's why the behavior of the semiconductors is totally different from insulators and metals, right? So here in this experiment we are going to calculate this energy band gap for the given material, for the given semiconductor, right? You can see here, you can go through this entire theory. Now what we are going to do in this experiment, actually we are going to take a p-n junction diode. We know very well that p-n junction diode has been made by taking suitable semiconductor, because p-n junction diode is a semiconductor device. It is made up of a particular semiconductor material, right? So as I was saying, that what we are going to do in this experiment, that we are measuring the reverse saturation current of the p-n junction diode at different temperatures. We know very well that when a p-n junction diode is reverse biased, right, it allow only very small current of the order of microamperes through it, right? And that current is because of the presence of minority carriers in both p as well as in n section of the p-n junction diode, and this current depend upon the temperature, right, and also on the energy gap of the that particular semiconductor that is used for making this p-n junction, right? So in this experiment, the whole experiment that we are going to perform, we are just measuring the reverse current of this p-n junction diode at different temperatures, right? Reverse saturation current. And then after we are going to plot graphs, right? You can see here in the theory, even if you can go through this theory in details, although you have gone through it in your solid state physics theory class, right? We know in reverse wise, the reverse saturation current of a p-n junction diode is given as Is is equal to A T power 3 by 2 e raised to power minus Eg upon Kt. Here A is a constant, T is temperature in Kelvin, Eg is the energy band gap, right? And K is Boltzmann constant, T is again temperature in Kelvin, right? So if I take log on both the sides, log base 10, then log 10 Is, now this term A and T, both these are constant. I can treat temperature as a constant when there is very small change in the temperature, right? Then AT is constant, so I got constant after taking log. Then this term exponential will go away and I will get minus. When I will solve this, I will get 5.04 Eg into 10 raised to power 3 divided by temperature, right? Now this is the equation that we are going to utilize. I am highlighting it. We are going to utilize it. We will measure the reverse saturation current at different temperatures. Then after we will plot a graph between 10 raised to power 3 upon T, or we can say 1 upon T versus log 10 Is, right? Because in this equation you can see that this Is, reverse saturation current, depend upon temperature. The other things are constant. Constant energy band gap is also constant, right? This is constant, so it depend upon T. So when we will plot a graph, right, we will get a straight line that will have slope 5.04 into Eg. So if we find out the slope from that graph, then by using this relation, Eg will be equal to slope of the line divided by 5.04. So this is the way of calculating the energy band gap of the semiconductor material that is used for making this PN junction diode, right? I advise you to go through this theory, right? This is the circuit diagram, very simple. PN junction diode is reverse biased. You can see here we have a power supply. We are going to apply some heating mechanism to this PN junction diode so that its temperature will change, and we will keep on measuring the reverse saturation current that is given here, microammeter, right? So this is the theory. Now pre-test. We have to do pre-test as we do usually in case of doing experiments here on the virtual lab. So the first question is the plot of 10 raised to power 3 divided by temperature versus log 10 Is. We know very well it will be a straight line. The current in PN junction diode is in during reverse wise is in a microampere, very, very small, right? Energy band case gap in case of silicon 1.5 1 electron volt. Energy band gap in case of germanium 0.7 electron volt. Submit the quiz, 4 out of 4, right? Then I am going to the procedure, right? I told you what is the procedure, but I advise you to go through it because it is somehow different for this virtual lab, but the thing is same, right? Then I am going to the simulation part, right? You can see here. So first of all, you will enable the power. Power is enabled. Among the now it is again asking you a answer. Among the following graphs, which graph is plotted for semiconductor in energy? This graph. This is the graph, right? So image 2 is the correct answer. You chosen the correct answer, right? Okay, right? Then place container. Now place container. When you will click place container, you will then click here. Container means this is used for putting the PN junction diode in this heating mechanism here, right? We will change the temperature of PN junction diode, right? Then we will take PN junction diode, click on PN junction diode, then click here. Now PN junction diode is placed here. You can see. Then what we need a battery. Battery, click on battery, then click here, right? What we need, ammeter, click on ammeter, right? Voltmeter, right? Voltmeter here. So I got all these components here, what I need. Now then I have to go for a circuit, right? So circuit is PN junction diode is reverse biased. So we will go from start from negative, right? So connect. You will put you will click on connect, then click negative, then click on a negative of ammeter, right? Clicked. Then positive of ammeter will go to this this side. Now PN junction diode, negative terminal of the battery is connected with the P side of the PN junction diode, and now you will go for the positive. Positive, you will go to the this side, right? Now positive terminal is connected with the this N side of the PN junction diode. PN junction diode is reverse biased. Now here don't take it that these two lines, these two wires are crossed here. They are not touching each other. What is it is shown here that these two wires are touching, right? So now I'm going to connect the voltmeter for measuring the voltage. So again, positive terminal, positive, negative terminal, negative, negative, and negative. It is not getting connected. Okay, it is connected, right? So now the connection is ready. I was telling you that you don't think that these wires or these connections are, mixed or they are touching each other, right? It is actually looking here that these are touching, but actually in practice they are not touching, right? So this is the way of connecting this circuit, right? Now the circuit is ready, right? I will place a thermometer here, right? Place thermometer for measuring the temperature. Thermometer is placed here, right? Now I will set the voltage. So voltage is 5 voltage of the battery. Voltage is set. Now what I am going to do? This is very important. I am going to set the temperature. Let the temperature is 90°C. I will measure the reverse saturation current. I will click here, but first of all, let's change the temperature. It is 85°C, right? And then after, I think there is some problem in the circuit. Okay. Okay, we have to first click here, click. Now it is ready, right? Now 85. I am starting from the temperature 85. So at temperature 85°C, I am going to calculate the reverse saturation current. So I am going to fill this sheet. Temperature is 85°C, right? You have to fill this sheet manually, right? It is 85 and the reverse 36.15. 36.15, right? So now at 80, I am decreasing the temperatures gradually. At 80°C, find 32.01. 80, 32.001, right? Then at 75, find 28.22. 28.22. 75, right? Then at 70, 24.80. At 70, it is at 70, 24.80, right? Then at 65, right, find 65, 21.71, temperature is 65, right? Then at temperature 60, find 18.93. 60. Then at 55, it is 16.44. 0.44 and temperature is 55. Then at 50, 14.21. Okay. Now this is the table that I have prepared. Now you can even start increasing the temperature from 50 to 85 or whatever temperature you want. You have to measure the reverse saturation current, right? That is appearing at this voltmeter at these different temperature, but you have to not look at the ammeter. Sorry, this is the ammeter. It will directly calculate the reverse saturation current, right? That is given by this relation. Then after you have to fill the table on only, right? Then calculate the data. Now the data, temperature in Kelvin, 10 raised to power 3 divided by this temperature T, right? Log 10 IS, all the things are calculated, right? Now what? We are going to draw the graph, right? But for graph, you can see here, from the graph, you can see here, whatever graph I shown you in the beginning, the same type of graph that I got, right? That I told you in the beginning, that the graph between that was the question in the beginning, right? That what will be the graph between the log 10 is and 1 upon t, or 10 raised to power 3 upon t. The same type of graph that we got here, right? Now we have to actually find the slope. So when I will take my cursor at any point, you can see the value of the x and y. The x coordinate is given you 2.873. You have to take the note of it, 2.873, and the y coordinate is 1.450, right? So you have to put these values here, right? 2.873, 0.873, and second is 1.450. Find slope. You are given the slope, right, automatically. Then energy band gap, as per the formula, it will be slope divided by 504. So slope is 0.703, and this is already given. Energy band gap is of the order of 0.13, right? So this is the observed value of the energy band gap, 0.139, right? So this is the energy band gap that is used for making this particular type of PN junction diode. So this is the way of doing this experiment. In labs, if you have this instrument available, even then you can perform the experiment, right? The procedure is same. You have to take in the that instrument, set up the connections, then after you have to switch on the heating device. You have to take the temperature around 70 to 80 degrees Celsius, measure the reverse saturation current, then start decreasing the temperature, right? Or start increasing the temperature and keep on measuring the reverse saturation current. And then after doing all these calculations, again formula is given here, right? And you can find out the value of the energy band gap, right? So here the answer is observed energy band gap for this particular type of semiconductor that is used for making this PN junction diode is this one, right? 0.139 electron volt. It is in a electron volt, right? So this is about this experiment, very, very important experiment of the solid state physics. Now, after performing this experiment, you have to go for the post test. So I advise you that when you perform this experiment, please do this post test in order to check your knowledge, right? So thank you very much.